Thanks for joining, everyone, and thanks to everyone joining online. So I'm really pleased today to welcome Katy Evans to the department, who many of you know. And today's talk is not just a seminar, but it's an award presentation. So Katy is the proud recipient of the 2022 Barrow Award, which is given by the Metamorphic Studies Group, which I'm currently chair of. Katy unfortunately couldn't attend the conference earlier in the year to receive the award, so she agreed to come to Cambridge instead to give today's talk. So yes, I'm thrilled to pass on the Barrow Award to Katy. So confusingly, as you can probably see then, the Barrow Award is actually a kyanite-bearing eclogite from Norway rather than something from the Barrow zones, which I've never quite understood, but anyway, it's a very attractive rock. And it's been sitting in soggy St Andrews for the last few years at Dick White's house. So he says it's re-equilibrated to Barrovian conditions. Anyway, so I thought I would just read out or paraphrase some of the citation that was written for Katy when she got the award, sort of means of an introduction, and then I'll give the floor to Katy. So Katy is a professor in the School of Earth and Planetary Sciences at Curtin University, where she has been based since 2007 as a research and teaching fellow, ARC future fellow, and professor. Katy completed her undergraduate studies and PhD here, on Acadian metamorphic fluid flow in East Central Vermont with our coffee drinker there, Mike Bickle. So Katy is an influential scientist who has conducted high impact research and made fundamental contributions not only to the field of metamorphic geology, but also crossing disciplinary boundaries into economic geology, building on her thermodynamic work into sulfide minerals. She's written several important, highly cited process-oriented papers on the role of fluids in orogenic systems, redox budgets, and sulfide minerals that are of importance for our understanding of orogenic processes, as well as gold mineralization. The most important fundamental contribution that Katy has made to the field of metamorphic geology has been in creating a foundation for understanding of how metamorphic fluids control redox changes in the deep earth. So certainly a very fitting talk today. So Katy's also become a world-leading expert on unraveling the complexities of serpentinization and deserpentinization through a long-running collaboration with Ron Frost. Due to her work on redox budgets, element cycles, and serpentinites, Katy has become recognized as a world leader in the role of redox processes and fluids in metamorphic systems. As the citation goes on to list what an outstanding teacher, mentor, and community contributor Katy has been. So she's currently the editor of my favorite journal, the Journal of Metamorphic Geology. And it finishes with, Katy stands out as an excellent researcher, mentor, teacher, and member of the metamorphic community. And we believe that the Barrow Award is a fitting recognition of Katy's outstanding work. So join me in another round of applause, and we'll let Katy.
Thank you, Owen. And hello. Thank you. And hello, people on the Zoom also. So yeah, I'm going to talk about redox processes in subduction systems. But first, I'm going to just say a huge thank you to the Metamorphic Studies Group and to Annie Tompkins, who nominated me to the award, and to Mike Bickle and Roger Powell, who supported that nomination. Like this award does mean a huge amount to me. It's my first award, probably my only award. So yeah, I'm incredibly grateful for the nominations and the time people put to support that. Also, because I'm in Cambridge, this is a really good time for me to just say a special thanks to Graham Chinner, who died late last year. But he was my supervisor from second year onwards in my undergraduate degree here. And I was thinking there's a few stories I could tell about excellent stuff that but then I realized quite a few of them he told me off, and so I won't tell those. But I will say, so between me submitting my PhD and during the examination, basically, me and a friend, Cynthia Robinson, we did some work sorting out the thin sections in the 1B lab. So I'm sure they're complete chaos again already. So, but this was a long time ago. This would have been in 1999, and But if you see yellow dots on any of those sections, we put them there. And there was a spreadsheet, but I'm sure that's long gone. But anyway, there were lots of rocks and there were lots of minerals, and some of them we'd never seen before. So I used to visit Graham regularly to ask, and I remember he showed me Vesuvianite for the first time, and I still remember that. So yes, he made a big difference to my life as a geologist, and here's a great place to acknowledge that and to remember him. So yeah, okay, so if you haven't read this fabulous paper on prolific gneisses with varying ferrous-ferric ratios from 1960, it was groundbreaking for its time, and still useful now. And when you read it, you realise that modern papers don't measure ferric-ferrous ratios anymore, and they report total iron. And whereas when we used to do not me personally, when people used to do wet chemistry, it was routine to measure ferrous and ferric iron. And if people still did that, then I think we probably know some quite fundamentally different stuff, because there's a lot of things where you kind of wonder what that ferrous ferric ratio is, but people don't measure it. I measure it. I'm lucky enough to be in Perth, where we've got lots of analytical labs, so you can just request it. Anyway, just a request to the community. More acknowledgements. I will start talking about science soon. The work in this talk was all collaborative with a bunch of people, and some of them get their pictures up. So hi, Andy, if you're listening, but probably given the time difference, you're asleep. Ros Crossley and Sarah Hayes did their PhDs on subduction zones, redox budgets. So some of the work I will present is with them, and Fiona's mother soul, who did her PhD on serpentinization in New Caledonia. So their work is acknowledged here. Okay, now onto the talk. This talk's based around a question, and that question relates to subduction. We know that most of the iron, carbon and sulfur in the Earth's mantle are as iron 2+, as carbon 0 or carbon -4, this is valences, and sulfur 2-. So those elements are all reduced pretty much in the Earth's mantle. Whereas the iron that we subduct, or that subducts in the serpentinized mantle lithosphere, in the altered ocean crust and in sediment, a much greater proportion of that is oxidized as iron 3, it's carbon +4 in carbonates, and more oxidized sulfur in things like pyrite and gypsum, which is a sulfate mineral. So the question that we have to ask is what's the consequences of this? What happens when we add these oxidized iron, carbon and sulfur to subduction zones? Where does it go? What does it do? So why would we even care about this? It's actually fundamental to a whole range of different Earth system processes. So for example, the pressure, temperature and composition of silicate melting, which has a direct effect on the formation of continental crust. That is a function of the redox state of the melt source to a large extent. This links into the formation of ore deposits. There's certain ore deposits where their genetic models require an oxidized source zone. For example, iron, carbon and sulfur are redox sensitive elements, so they can take the different oxidation states, and redox reactions are essential for life. You know, we're carbon-based organisms, and if we don't have iron and sulfur cycling, it you know, all goes bad quite quickly. We know that the planet has evolved from a relatively homogeneous ball of hot dust into something that has got a core of iron as iron 0 and a atmosphere where any iron in equilibrium with that is as iron 3+. So the temporal evolution of our planet is a process of electrochemical differentiation and redox zoning, which subduction zones are trying to keep mixing up. And then if you want to look at the hazard side of it, a volcano emitting H2S, for example, is much more deadly than a volcano emitting SO2. And the climatic consequences of those are quite different as well. So for many, many reasons, we would like to understand the consequences of subduction. So there's far too many of those to talk about here. But I am going to say a little bit about how we would study redox processes in subduction zones. And obviously that means we have to visit the mantle. And here it is in New Caledonia, in the New Caledonia ophiolite, where it's conveniently exposed for us. We'll then look a little bit about how big the fluxes of redox sensitive elements are, what they might be able to do to the interior of the Earth. And then we'll focus in a little bit on sulfur and ultramafic rocks because they're interesting. So, subduction is an open system process in that you have inputs and you have outputs. Most studies of redox in geological systems use a parameter such as oxygen fugacity. You might see hydrogen fugacity. You might see a range of different variables, and most of them are intensive variables, which you may probably all know what they are, but I'm going to tell you anyway. Intensive variables take the same value throughout a system at equilibrium, and they're independent of the quantity of material that you have. So they're incredibly convenient. Things like temperature and pressure are great for the study of metamorphic systems. FO2 is a great parameter as a monitor for the redox state of a system that is undergoing some kind of metamorphic or igneous process. However, if we want to study fluxes, then a parameter that is independent of quantity is clearly going to be suboptimal. We need something that depends on quantity, and that means we need an extensive variable. Every intensive variable has an extensive conjugate variable, and by taking a kind of a nuanced view of what we want to measure and how we want to look at things, we can choose the appropriate variable for the system that we want to look at. So where we've got to is that if we want to look at fluxes of redox sensitive elements in subduction zones, we definitely need an extensive variable. What else does it need? Because we're sticking down a whole range of different redox sensitive elements like iron, carbon, sulfur. You can include oxygen, hydrogen, arsenic, vanadium, manganese. You can include those as well, but they're less smaller fluxes. But what happens is that electrons switch between those different elements during subduction and whatever happens after that. So it's not so useful to look at the flux of a single element when you're looking at the total consequences of the addition of this oxidizing capacity. So we want to have a variable that combines the oxidizing capacity of multiple elements. Also, if you add oxidizing material to an environment that's already oxidized, you're not actually going to change its redox state all that much because it's already kind of buffered. So if you add more of that buffer, all you get is a bigger buffer. So we want to be able to use a reference state that shows us the effect of whatever we're adding relative to the conditions within the reservoir to which it's being added. And I probably didn't say that very well, but I'll tell you what's in the equation and then hopefully it'll make sense. So we're going to use a variable called redox budget, and that's RB. And it's the sum of the different elements. That means it combines the oxidizing capacity carried by multiple elements. It's a sum for all the different elements. I can't believe this is a very simple equation for Cambridge, but never mind. It's the number of moles of that element in the oxidation state that you're considering, multiplied by the number of electrons that you need to add to it to take it back to the oxidation state of your reference state. And basically, the larger the redox budget, the bigger the oxidizing capacity of whatever you're considering. So I'm just going to go through one of these examples. This one, the middle one. So say we've got 2 moles of iron oxide, where the iron is iron 2 and the O is 2 minus. And we've got a reference state where the iron is iron 0 and the O is O2 minus. Then to get the iron 2 plus to Fe0, we have to add 2 electrons to it. And because the 2 moles of the iron, that makes, and the oxygen's in its reference state already, that means the redox budget of that is 4 moles. And I should have put the units there, but I didn't. So that's redox budget. So let's apply it. This is a really simple conceptual model for a oceanic subduction zone. We haven't looked at continental subduction zones yet because there's a whole load of complications and we don't really understand the oceanic ones yet. So let's just stick to the simplest possible conceptual model that we can. We have inputs in the form of sediments, alteration, crest, and mantle lithosphere. We have outputs. The redox budget goes into the subduction zone. It might come out to deep mantle, might end up transferred to the mantle wedge, or it might be emitted in volcanic gases or non-volcanic kind of outputs to the ocean and atmosphere, or it might end up in the lithosphere related to arcs. We have very little idea still of what kind of fluxes might be going on between these. So I'll put a box around them and they're all in the same box. But I will go a little bit into the transfer between the subduction zone and the mantle wedge later. Then do some quite simple flux calculations where a flux is the mass flux of the host rock multiplied with the proportion of the element of interest. We only looked at iron, carbon and sulfur because most of the rest don't. The redox budget carried by those elements is order of magnitude smaller than by these big 3. You can get reasonable estimates for most source rocks and most of the elements from the literature, but serpentinized mantle lithosphere, when I did this work, there wasn't all that many measurements of it, and certainly not of the ferric ferrous ratios. So for that we use some serpentinites from New Caledonia and also from the Mid-Atlantic Ridge. And the uncertainties were propagated. Otherwise, I wouldn't be able to do this talk in front of Mike, would I? That would be too embarrassing. So Owen mentioned Ron Frost in the introduction, and there he is looking at some serpentinites in New Caledonia. And as you can see, they're quite heterogeneous, which basically means that the more you look, the more you start to see how these systems are quite complex. But we'll go back to the simple approach. I'm going to summarize the results here. This is a plot of the fluxes on the y-axis against the element fluxes for iron, carbon, and sulfur, and the redox budget flux on the right-hand side. The green bar is the net addition to the subduction zone. So that's what goes into it minus what comes out of it. And then, because obviously we have a global system where we have outputs from in mid-ocean ridge basalts, ocean island basalts, we included those as well to get a total output. So if the pale green bar and the blue bar kind of match, then you're looking at no net addition of whatever you're looking at the subduction zone. These are the error bars, and you can see that iron, carbon, and sulfur within error, they all balance. Whereas if you look at redox budget, which has a massive uncertainty because there's a lot of things we don't know, but you can, and that's I think is the Monte Carlo uncertainty. They don't balance. So we probably are looking at an addition of redox budget to subduction zones via subduction processes. So that's cool. We can break that down a little bit. So first I'm going to show you if we minimize all the estimates. So we have a small, tiny effect on increasing the redox budget of deep earth by subduction. And we separate the inputs from sediments, altered ocean crust, and mantle lithosphere. We separate the outputs into arc rocks, arc gases, and non-volcanic outputs. So that's all the 4-arc business. If we dial all these down, dial all these up, then we return 77% of our redox budget, and we stick down a few times 10 to the 12 moles per year. If, on the other hand, we dial everything up, so we maximize the inputs and minimize the outputs, then mantle lithosphere shoots up to be the biggest contributor in front of altered ocean crust, and the non-volcanic gases actually start to contribute to oxidation of deep earth, because that's negative, because they're full of methane, and you're only looking at the return of 1.5%. And if you do the Monte Carlo estimate, which is basically running the calculations over and over again with a randomly assorted choice of inputs, then you're looking at about 27% return. So I think we're reasonably confident that we're oxidizing something by subduction. Now, we don't really know what that is. It could be the deep earth, but something that's of particular interest is how some of it may be transferred to the subarc mantle. And the reason that this is of interest is that we know that the subarc mantle seems to have a higher oxygen fugacity than mantle elsewhere. And that's from measurements of arc outputs. It's also from measurements of xenoliths that come up, and a bunch of other things that Helen knows a lot more than me, so I shall move on swiftly. And this has been linked to the formation of arc-related ore deposits, because we know that there's a few genetic models of things like porphyry copper that require an oxidized source. It's not entirely uncontroversial. There are certain trace element ratios that say that maybe the source of arc rocks is the same as the mantle elsewhere. But increasingly it does look like you've got an oxidized source. So, and what's right next to the subarc mantle? A subduction zone. And what's in a subduction zone? All this oxidized stuff. So does it transfer? If we look at how it transfers, we're then limited by the solubility of things like oxidized iron and carbon dioxide in subduction zone fluids. Most of them aren't very soluble. So you're limited to 1 to the 3, a few times 10 to the moles per year. But we can still look at that. Is it enough to do much? So here's a conceptual model, another one. Here's a subducting plate, here's an overriding plate. This flux is in of redox budget, flux of redox budget out. It mixes with the mantle outside. You've got a plumbing efficiency that can vary. Is the fluid flow into the subarc mantle very focused towards the source of the arc rocks, or is it quite pervasive and diffuse, so it's not really very effectively sampled? And how tightly is the input and the output coupled? So if we put redox budget in, does it go straight out again, or does it build up? So that made a very simple expression. And we looked at the Phanerozoic, because before the Phanerozoic, when like atmospheric oxygen levels were much lower, I did the calculations and pretty much nothing happened. You could subduct whatever you liked and nothing much happened. So again, on the left, we've minimized the effects. On the right, we've maximized them. So on the left, we've said that the plumbing system is very diffuse. We might be adding redox budget, but it's not necessarily going to the source of the magmas, and it's very strongly coupled. So as soon as we add the redox budget, it comes out again in the volcano. We've said this is what you get if your subarctic mantle is very strongly buffered by having sulfur in it, for example. This is what happens if it's quite weakly buffered, so it's got water in it, and it's quite keen to transfer the redox budget. So if you minimize the effects, then we can see increases in the oxidation state of the arc magma source zone of the kind of values that we think we might be getting, which is around here, about 1 to 2 log units above the FMQ buffer. And we see that happening on the kind of tens of million years timescale. If we look at it in the case where we maximize the effect, we can see that we easily get the effects and some really quite big ones, and that happens on the hundreds of thousands of years to million years timescale. That's quite cool. And since we did this work, people like Mary Jo Brown's have been looking at the rate at which subduction components come through. And she's looked at redox specifically. And I think there's some Turner and Hawksworth work that put the transfer much more in this side of things than that side of things, in the 10 to the 5 to 10 to the 6 years. So that's fine. We like that one. So to summarize where we've been so far, yes, we can start to put some first order constraints on subduction zone redox budgets. The iron and carbon and sulfur do balance within error, and it's likely that there is a net addition of redox budget by subduction to the mantle, but the fate of that was largely unknown in 2012, and is still largely unknown, which is great, because otherwise, obviously, life would be very dull. So we still don't know whether it goes to deep earth. We still don't know if it does get to subarctic mantle, how it gets there, and it's certainly plausible that the high FO2 that we probably see in subarctic mantle is related to subduction zone additions, and the sort of the idea where we have this quite focused flow and transfer of redox budget has some support in independent observations. Okay, so moving on to focus on rocks a little bit more, and we're going to look at ultramorphic rocks because I like them, and also because there's massive fluxes. We don't know quite how much of the mantle lithosphere that is subducted is serpentinized, because it is really heterogeneous, and quite a lot of it happens where the slab bends to go down into subduction zones and water percolates there, but we don't really know how much. And the geophysicists have been quite slow in telling us the answer. They may have other priorities. I don't know why that would be. We do know that serpentinites are obviously hydrated. It comes in the name. A lot of them have carbonated. A lot of them have a lot of magnetite in them. So potentially they transfer a lot of redox budget with potentially significant consequences. So we did rock specific studies in a few different ways. Firstly, we used ThermoCount, a rather marvelous program with a great database, using bulk compositions from the New Caledonia ophiolite, incorporating sulfur and carbon bearing phases. And what we did was we calculated pseudosections, which basically showing the mineral assemblage as a function of pressure and temperature, and looked at the variation in not just mineral assemblage, but also redox budget as a function of pressure and temperature on hot and cold isotherms to subduct. That's wrong. Hot and cold subduction trajectories and in open and closed systems, because there's also a open system calculation in thermocount. So this is a pseudo section. This is temperature to 850. This is pressure to 5 kilobars. It replicates what we know about the pressure temperature relationships of ultramafic rocks. So we have brucite dehydration running around here. We have serpentine out running around 600, 650. Then we have a sort of bit of chlorite knocking around, and that goes out at higher temperatures. Carbonate, some forms of carbonate stable over the whole thing, except for the very highest temperatures. That again is consistent with what we know about suspected ultramafic rocks. And in terms of sulfide phase, we have pyrrhotite around here, and then pyrite over here. Because basically, as the minerals get the balance of iron and magnesium shifts, because olivine is more iron rich than serpentine, so that's going to stable pyrite over pyrrhotite. And it's an effective bulk composition shift, and the competition between the sulfides and the silicates. So some of the closed system calculations were done on the hot and cold subduction trajectories, and the open system calculations were done on an isotherm because they were quite time consuming, so that was quicker. This was a cool, I thought, output of those calculations, which is, so this is done at a fixed pressure, I think it's 2.4 GPa, and it's temperature against redox budget, and I contoured it for the deviation of the redox state from the FMQ buffer. So this is 2 log units below FMQ, this is 5 log units above FMQ. And the reason that I've showed it you is because I want you to notice that if you fix the redox budget, so nothing changes, you can go from a rock that you would consider to be quite reduced at FMQ minus 1.5, increase the temperature, and it ends up at plus 3.5. And that's something that you tend not to think about when you're always thinking about oxygen fugacity, in particular oxygen fugacity relative to one of these buffers, is that the trajectory of the rock may not be parallel to that buffer. So you can forget everything else that you've heard today, but I would like you to remember that if you're inclined to do so. So the results are, we looked at hydrogen, water, carbon and sulfur with the open system calculations. All the water's lost, as you would expect when you take pentonite and you turn it back into a peridotite. Only 5% of the carbon was lost. And that happened in a little jump at brucite out and a bigger jump at antigerite out. And that's these two. This is brucite out, this is antigerite out. And with sulfur, only 1% was lost. But again, it's lost at those two main reactions where the water is lost. So the rock is always reacting in a kind of multivariant kind of way. But it's at these main low variance reactions that we see the loss of water, carbon and sulfur, but not very much carbon and sulfur. This is the redox budget for those same calculations. That's redox budget, that's temperature. This is the redox budget of the increment of fluid that's knocking around. So there's never very much fluid at one time. So it's always quite small. But at brucite out, there was a bit of methane in the fluid. So it popped down to be a little bit negative. Not much happened at antigerite out. But that is changing a little bit, because what we see is that the redox budget of the rock actually increases with methane loss, and then it increases again with the loss of reduced sulfur as hydrogen sulfide. So this is pretty rubbish as a rock that is going to release redox budget into the subduction zone system, because if it was going to do that, the redox budget would be decreasing, but this is clearly increasing. So that was quite an interesting result. We'll go into that in a minute. So for that particular rock, we probably have to predict that the carbon and sulfur are probably, and the redox budget are cycled into the deep earth, and that methane loss would actually decrease the subduction zone of decrease the redox budget of wherever that methane ended up. This was published in 2015, and since then there's been a bunch of different models of serpentinites and what happens to them in subduction zone systems. And some people, their results are very similar to this. Some people like, oh no, they can oxidize anything they like. So there's been a real diversity in terms of the kind of results that people get from modeling serpentinites, which is interesting. So we're going to explore that a little bit by looking at the effect of the geodynamic setting of serpentinization. So you get serpentinites formed in a whole bunch of different settings. You get abyssal serpentinites where you get interaction between hydrothermal fluids or ocean-derived fluids in a mid-ocean ridge or similar setting. The slower spreading the ridge, the more likely the interaction. We see serpentinization where we've got ophiolites from the overriding plates, like the ones in New Caledonia, and we get mantle exposed at extended margins with ocean continent transitions. Then they can be metamorphosed and exposed in places like the Alps, and then we can see hybridized serpentinized peridotites where they're close to, for example, a Barrowic unit, and then the hydrothermal fluid flow will give you some quite interesting metasomatism, things like calcium mobility and stuff like that. So serpentinite is not just a serpentinite. They may have really quite a restricted list of elements. You know, you can pretty much model them in iron, magnesium, aluminium, water, and then add CO2 and sulfur if you like. But you can get the main reactions in a very restricted chemical system, but they are extremely diverse for all that. So to look at these, we did something slightly different because we were really focusing on the opaque minerals in these rocks, which meant we needed to think quite a bit about nickel in minerals like hazelwoodite and pentlandite, and we needed to look at things like the iron nickel alloys like awaruite, which is iron nickel 3. And so put some thermodynamic data together in that system, iron nickel, oxygen, hydrogen, sulfur, and then use that to make activity diagrams, and then just map the different opaque mineral assemblages that we saw. So these are some of the lovely textures that we see. These opaque minerals are quite accommodating in that you see things like this is hazelwoodite surrounded by magnetite. There's some pentlandite sitting over here. So that's metal rich and sulfur poor. That records the early stages of serpentinization. You've got millerite over here, which is where the metal to sulfur ratio is much higher. So it's that they are recording the changes, and that's from the Gressoney shear zone in the Alps. This is from New Caledonia, Gressoney, New Caledonia. Anyway, the textures are absolutely stunning. And this is the iron alloys, so you can see those with magnetite here as inclusions in magnetite there. So what happens when we put those onto activity diagram. So this is the activity of sulfur against the oxygen for gassity, the ideal variable in this case. This is the phthalate magnetite quartz buffer. This is where hematite, magnetite, and pyrite coexist. This is where arylite, magnetite, pentlandite, and hazelite coexist. These are the mineral assemblages from the Mid-Atlantic ridge, and the early ones are quite reduced, and the later ones are more oxidized, so they kind of come up this line, and we see this modification with progressive subpentonization. If we look at New Caledonia, everything was in the much more reducing part of the diagram. We looked at the samples we had from the Zermatt SAS, they were all in the much more oxidizing part of the diagram. This is from Ros Crossley's PhD. She looked at serpentinites from Corsica. And I'm not going to go into detail with what you can see here, but you can see the arrows are basically going all over the place, which tells us that it's a complex business, serpentinization, and that there's computing processes, and you can take a bunch of different paths through both serpentinization and deserpentinization. So if you think you know what's happening, you're probably wrong. This then kind of motivated the idea of, well, let's look at pseudosections for different types of serpentinite. So this is a pseudosection for an oxidized serpentinite. It's a slightly different bulk composition with the sulfur from the New Caledonian rocks, and obviously with water added to make it a serpentinite. And to do this one, basically, I jacked up the ferric iron as high as I could without losing the fundamental reactions that make this very recognizably a serpentinite pseudosection. Hasn't got carbon and sulfur in it, because they weren't the main items of interest in this case, and they wouldn't make much difference to the results. So temperature, pressure, it's contoured for the number of log units difference from FMQ. So we've got 0 over here, so this bit's at FMQ, this bit's at FMQ plus 5. This is brucite out, antibarite out. This is a Syracuse subduction geotherm, and what you can see is that nothing much happens to start with, but by the time you get to antibarite out, you are up at FMQ plus 4. And what these various works on deserpentinization over the last few years have shown is that if you're up at FMQ plus 4, then the sulfur speciation, your sulfur is as sulfate, and that is an excellent candidate for transferring redox budget. So for your oxidized serpentinite, sure, it can transfer redox budget. Do the same calculation for a reduced serpentinite, bringing the ferric iron to total iron right down. Same business, pressure, temperature, contours relative to FMQ. And this time, by the time you get to antibarite out, or you're at FMQ plus 1-ish, so you are not, all your sulfur, should it even get into solution, would be as hydrogen sulfide or another reduced species. It would not be transferring the kind of redox budget that you need to oxidize the subarc mantle. So this was quite an interesting result. We can bring peace between the people who think that serpentinites oxidize and don't oxidize the subarc mantle, because it depends what kind of serpentinite that you have. So that's good. So we're coming to the end now, which is good. we know that now that serpentinites from different geodynamic settings track differently through pressure, temperature, redox budget, space, and reduce different fluids. Something that did come out of this work is relates to representative sampling, because if you look at the work on serpentinites, there's a lot on the Alps, and you look at the serpentinites in the Alps, and a lot of them are from these extended continental margins, and they're the most oxidized serpentinites that I've ever seen. So it's a note of caution there, I guess, on what you look at. And obviously, because I live in Australia, did I go to the Alps to sample serpentinites? Not initially. I went to New Caledonia because it was much closer and nice. Not the Alps isn't nice, it's lovely. But yes, it's what you sample can affect what you see. All right, so to finish with a bit of an outlook, nothing has suggested that the slab is probably the cause of oxidized art products, but it may well not be serpentinites, because okay, oxidized serpentinites will make oxidized fluids, and they can carry sulfate. But if you look at what we're subducting today, most of it is oceanic crust that is formed at relatively fast spreading ridges. So the serpentinites that are related to those are quite unlikely to be all that oxidized. So that still leaves the question of the source of redox budget quite open, and the species that transport it. We don't know enough about aqueous speciation in high pressure fluids because they're quite hard to study. But then when you start to add in the fact that you don't just get aqueous fluids in these settings, you also start to get your supercritical fluids, you start to get silicate melts, which can carry quite a lot of ferric iron. What happens when, say, an aqueous fluid from a serpentinite interacts with maybe a sort of like low percentage partial melt from sediment, stuff like that? What happens to those speciation? What happens in the subduction channel? It's a crazy place. And if redox budget actually gets to the mantle wedge, then how does it move around? I don't know any of these things. That's why it's outlook. But we do have methods to do so. And I think that's all I have to say. Thank you.
Excellent, thank you. So we have plenty of time for questions. And Oscar, are you monitoring? Yeah, excellent. So we'll start with questions in the room. So Mike.
So really what matters is what oxidizes or doesn't oxidize the serpentinites or ocean crust in the first place. And so, I mean, why I'm asking that is what's always interested me is what oxidizes the ocean crust, because the main oxidizing agent in the ocean is sulfate. And there's a big question, how much of that is deposited as anhydrite in the ocean crust, and how much oxidizes the silicate assemblage? It seems to be moderately oxidized.
Yeah.
Could you paraphrase the question just for the
Yeah, so Mike said what oxidizes the ocean crust, and he mentioned that there's quite a lot of sulfate in seawater, which has the potential to pass on some redox budget, and also that we know that we do get some gypsum in altered ocean crust, but it seems to be quite a heterogeneously distributed. And is that what you were saying? Is that the question?
Basically, yes. I mean,
yeah.
Sulfate, how important is sulfate reduction in the ocean crust? And how does this all matter to your oxidization and the species in the serpentinites, I guess?
Yeah, I think it's that is a really good question, and I would probably say that for the altered ocean crust, for sort of like Gabbro's sheeted dikes and states, so on and so forth, then sulfate is absolutely the most important vector for the transfer of redox budgets, because we do know that we have gypsum in those rocks. I mean, I know it's got retrograde solubility, so it can go out quite early, and I know that you can look at one set and it will have quite a bit of gypsum, and you look at another lot and it will have not so much, but basically you have transferred that sulfate to the altered ocean crust in quite large amounts. So I think for altered ocean crust, sulfate is probably quite important. For serpentinites, probably not so much, because serpentinization, it increases the it does increase the sulfur content of serpentinites a bit, but not heaps. Nothing like altered ocean crust. But what you do get with serpentinization is that because the serpentine minerals have a higher Mg number than the olivine and orthopyroxene that they form from, is that you have all this iron knocking about, this homeless iron. It wants to be in a silica, it can't be in a silica, so you form a lot of magnetite. You also form things like brucite and the iron alloys, but by the time you get to the end of serpentinization, you end up like your final product is a serpentine magnetite rock a lot of the time. So, and that redox budget, I actually think, just comes from water to a large extent. I don't think that's from sulfate.
So you lose hydrogen, basically.
I think, yeah, because the serpentinization reaction, you produce hydrogen. So you water goes in, hydrogen comes out, the redox budget stays there. The order of things I'm not quite so sure about, because some of it seems a little bit counterintuitive. So yeah, I don't really know beyond that. But I think sulfate's tremendously important in the altered ocean crust and potentially in sediments, and I think water might actually be quite an important oxidizing agent in serpentinites, just because it gets reducing enough to make hydrogen, and then the hydrogen goes away. So does that answer your question?
Yes. I don't know.
Oh, great, Tom, thank you. So build something I've been wondering about for a long time is what might control the oxidation state of serpentinites through time. I mean, the problem is, I tried, you might know this with Batiste, we tried looking for this, but everything was, well, totally altered. It was really difficult to convince ourselves we saw real variations. But we, even if we did, we weren't quite sure why there should be loads of oxidation state. But your point about getting totally different results from, say, alpine serpentinites in New Caledonia now makes total sense. But it would then be interesting to know what controls the secular variation, because that could be so important for thinking about, say, critical metal deposits and metal transport and all that jazz.
Yeah, doesn't it? Yeah, I mean, I probably the first thing. Did
Just
you?
a question again.
Oh yeah, hello Zoom people. So Helen said, what about temporal evolution of the kind of redox effects of serpentinization through time? And it's something that's quite difficult to study from rocks because they're all altered, and obviously studying serpentinites, we're used to our rocks being altered, but there's alteration and alterations, isn't there? So yes, because the I've seen very old serpentinites and their stuff, they don't remember really, they don't know what's happened to them. So if I was, and I agree with you that it could be tremendously important, because it's a sticking magnetite into the ocean crust is, yeah, you know, what's it into the deep earth or whatever. But I think what you could do is you can model serpentinization going with ocean water at present day atmospheric oxygen and 10%, 1%. Did you do that?
No, we were trying to do it on just actual measurements of rocks. I mean, we did speculate about the GOE, but then that became a more complicated thing, because then it's not just amount of oxygen, it's also amount of iron and amount of sulfur in the water and their relative oxidation states.
Yeah.
and then at least run out of money and push back to France and all that stuff.
Yeah, it's, a lot of the good questions are longer than 2 years or 3 years, aren't they? Because you see these diagrams of like ancient ocean waters and the speciation of iron, the ones that you get in papers about the formation of ore deposits and Mississippi Valley type or sediment hosted ore deposits. And I mean, just fundamentally, the ocean was such a different place. If I had to answer the question, I would say it was different, but I don't know how. Yeah.
Charlie, and then we've got one.
Yeah, my question kind of follows nicely on from Helen's. So that's good. So at the very beginning of your talk, you showed a time series with various ore deposits of gold and copper on it.
Yes.
And some of those are going to be before the Great Oxidation event.
Yes.
Are those associated with local oxidation? I know you showed serpentinites in the Alps are much more oxidized than New Caledonia, for example. Yeah, because some of those are really old there, like Sclavia superior sort of age. Are those porphyry systems or at least similar mechanisms? I don't know much about that.
Yeah, so the old porphyries, well, basically most of the porphyries on Earth are young.
Yeah.
And there's the argument, it's all about preservation potential because they form in the sort of roots of arcs, and they're potentially not something with great preservation potential. And I'm sure there's people in this room that can speak to that better than me. There are a few old ones. And we know that the great oxidation event sort of proceeded with like bits of oxidation, and then it kind of shut down, and then it came back again. So maybe, I don't know. I mean, if we had banded iron formations on here, then we wouldn't be able to have the type of convergence. But they really are an ocean chemistry dependent group of ore deposits. I think potentially the processes that form orogenic gold have actually changed over time, and there are redox aspects of that, but they're more related to local rock chemistry and structures and much stronger control. But I think the publication that I took this diagram from had that, so I included it. And because Australian audiences really like to see their ore deposit stuff. When you say, why do we care if it hasn't got ore deposits in it? They're like, no, we really don't. And then again, I think with epithermal, I think you're really looking at a preservation potential thing, because it like where they don't survive. So does that answer your question?
Yeah.
A bit.
Yeah.
I think I might have gone off the point a little bit.
That's fine. That's good.
Yeah, and I think did I forget to summarize it?
Apparently they can hear the questions quite well, so it's fine.
Oh, excellent.
And Charlie, Oscar was there.
Yeah, there are a couple of quick ones on Zoom if we have time. One is from Claire, Barbara and Elisa at the Open University, saying, how important is the subducted oceanic crust compared to the subducted serpentinized mantle, or is it volumetrically unimportant?
So the first one was altered ocean crust.
How important is the subducted oceanic crust compared to the subducted serpentinized mantle?
Yeah, I don't know.
Don't know.
Yeah,
Okay.
I think that's something that we will know fairly soon. But I don't know.
Okay.
Yeah.
The next one, Zoom. There's a question from Lucy Tweed asking, she's saying, you suggest sediment melts might be important for oxidizing the wedge. From a mass balance perspective, is there a sufficient redox budget for sediment melts to be the main oxidizing agent?
I don't think they would come with it. It wouldn't be something they brought with them, but they may be a transporting agent from it. So, for example, if a sediment melt met a magnetite-rich unit or fluid or something, I think they can. The melts are the things that can transport ferric iron. But they may not. I don't think they can actually. I don't think the melts that form would have enough in it. I think there would need to be a two-stage process for them to be effective. That's my answer. Does that? Yes. Yeah.
Excellent. All right, well, I'm conscious of the time, so we'll leave it there and give Katy a big round of applause.